Today in this lecture we are going to discuss the integration along a branch cut and analytic continuation. So first off I want to see the integration along a branch cut. As we know that the residue theorem can often be used to evaluate the real integrals when the function fz that is introduced has a branch cut. For examples, we shall evaluate here the improper real integrals the improper real integral integral from 0 to infinity x power minus a upon x plus 1 dx, where 0 is less than a is less than 1, x is greater than 0, which is important in the study of gamma functions. Note that the integral, say this is first, is improper not only because of its upper limit of the integration but also becomes its integrand has an infinite discontinuity at x equal to 0. The integral converges when 0 is less than a is less than 1. The integral converges when 0 is less than a is less than 1. Since the integrand behaves like x minus a near x equal to 0 and like x power minus a minus 1 as x tends to infinity, we do not however need to establish convergence separately for that which we contend in our evaluation of the integrals. Now let Cp, C rho and Cr denote the circles mod of z equal to rho and mod of z equal to capital R respectively, where rho is less than 1 is less than R, and we assign them to orientation shown in the figure. Since the branch, let fz equal to z power minus a upon z plus 1, where mod of z which is greater than 0, 0 is less than argument of z which is less than 2 pi. This is the multi-valued functions with branch cut. argument of z equal to 0 is piecewise continuous on C-rho and CR the integrals integral over CP 0 fz dz and integral over CR fz dz exist. To obtain that expression, we consider the closed contour indicated in the figures, that is traced out by a point moving from rho to R along the branch cut for fz, next around CR back to R, then along cut to rho, and finally around C rho back to rho. Then we draw the figures like this. Suppose this is my imaginary axis, this is the real axis, this is the suppose small circle, this is the origin z equal to 0, and 0 rho with the radius, z equal to -1 here singularity, this is the circle CR of radius capital R. So the radius is here capital R. This point, the orientation is like this, and this distance, this radius is rho. This is the branch cut. This line is branch cut. First of all, we start from these points and goes to like this, and from this point to these points again meet at these points R, and again from this R we come here and revolve about these points and reach at these points. So the orientation is like here, like this. We can write fz equal to exponential of minus a log z upon z plus 1. This is equal to exponential of minus a log z ln r plus I theta upon z means r into e के power I theta plus 1, since z equal to r into e के power I theta, and use theta is equal to 0, and theta is equal to 2 pi along the upper and lower edge respectively of the cut annulus. We see that fz, this must be exponential of minus a ln r plus I into 0, theta is equal to 0 here, divided by r plus 1. If we put here theta is equal to 0, this gives 1, and this gives r power minus a upon r plus 1, since z equal to r into e का power I 0. On the upper edge. And fz equal to exponential of minus a ln r plus I 2 pi upon r plus 1, and this is equal to r power minus a into e का power minus I 2a pi divided by r plus 1. Z equal to r into e का power I 2 pi on the lower edge. Then by residue theorem, the suggest we have capital R power minus a upon r plus 1 dr plus integral over cr fz dz minus integral from rho to r power minus a into e power minus I 2a pi divided by r plus 1, and here dr plus integral over 0 fz dz. This is equal to 2 pi I into residues of fz at z equal to minus 1. So this is equation first. Here phi z equal to z power minus a, this may be written as exponential of minus a log z since mod of z which is greater than 0, 0 is less than, argument of z is less than 2 pi is analytic at z equal to -1. And that phi of -1 is equal to exponential of minus a ln1 plus I pi, and this must be e power minus I a pi. This shows that the point z equal to -1 is a simple pole of the function f z. So residue at z equal to -1 f z this becomes e power minus I a pi. Thus from equation 4 first we have integral over c rho fz dz plus integral over cr fz dz. This is equal to 2 pi I e का power minus a pi I plus here common is e का power minus I to a pi minus 1 into integral from rho to r power minus a upon r plus 1 dr. Now we see that mod of integral over 0 fz dz, which is less than equal to here mod of fz, that is from here we get a rho power minus a divided by 1 minus rho, and mod of dz, that is circumference of the circles, small circles of radius rho, so it gives 2 pi rho, and this is equal to 2 pi upon 1 minus rho into rho power 1 minus a, and mod of integral over c fz dz, which is less than equal to r power minus a upon r minus 1 into circumference mod of dz, that is 2 pi r. This gives 2 pi r upon r minus 1 into 1 upon r power a. Since 0 is less than a is less than 1, the values of two integrals tends to 0, as rho and r tends to 0 and infinity respectively. So from equation second we have let rho tends to 0, so we write integral from 0 to r power minus a upon r plus 1 dr. This must be 1 upon e power minus I 2a pi minus 1 into integral over CR fz dz minus 2 pi I e power minus I a pi let r tends to infinity, then we have integral from 0 to infinity r power minus a upon r plus 1 LDR. This must be 2 pi I into e power minus I a pi divided by 1 minus e raised to the power minus I 2a pi, which is same as integral from 0 to infinity x power minus a upon x plus 1 dx. This is equal to pi upon sin a pi, where 0 is less than a is less than 1. This is the required results. Next, analytic continuation. Suppose a function f1z is analytic in a domain D1, then there exists a function f2z which is analytic in the domain D2, such that f1z equal to f2z for each z in the intersection of d1 intersection d2. Then f2z is said to be an analytic continuation of f1z. For example, a figure is this. Suppose this is domain d1. Here f1z is analytic in this domains and their functions. Let this is domain d2. Here another function f2z is defined, which is analytic in this domain d2, and the common portion is this. Here in the common portion f1z equal to f2z for every z. Then f2z is said to be analytic continuation of f1z. For example, let f1z equal to 1 upon z, where real object is greater than 0. The domain of the definition real object which is greater than 0 is denoted by d1. In the figure. And f1 is analytic there. Here f1z is not analytic at z equal to 0, that is at the origin. Let f2z be defined in terms of geometric series. f2z equal to I summation n equal to 0 to infinity z plus I upon I power n, where mod of z plus I which is less than 1 within its circle of convergence. Which is the unit circle centered at the point z equal to minus I. The series is convergent. Since f to z, this is equal to I. If we put n equal to 0 here, then we get 1, n equal to 1, that is z plus I upon I. So common ratio will be z plus I upon I. So the sum of this infinite series, geometric series, will be Sn infinity, that is a upon 1 minus r. A, that is 1 upon 1 minus r, means z plus I upon I. Now solving this, we get here 1 by z. When z in the domain, mod of z plus I, which is less than 1, denoted by d2. Then f to z, this is equal to f1 z for each z in the intersection of d1 intersection d2, and f to z is said to be analytic continuation of f1 z, and the figure is as follows. Let this is my real axis, this is imaginary axis. This is the origin. Here minus I, and this region is d2, and this is real of z is greater than 0, that is suppose this region, this is suppose d1. So common portion is this. Minus I is this point, suppose. And the region is suppose here d3. This is d1, this region is d1, this region is d2, and we can say this region is d3. In the common portions, we see that f1z equal to f2z. So f2z is said to be analytic continuation of f1z.